Okay, welcome back. Because school is canceled today, I'm gonna be doing a recording and you can all watch it whenever is good for you. Okay, so for this recitation, we're gonna be finishing amortized analysis, and then we're gonna be going to the next recitation, which is gonna be in the next video, which is gonna be linear data structures. So in this in this video, we're going to be doing amortized analysis, just a couple of examples that we didn't finish in the last recitation. So here we go. Just a reminder, amortized analysis, we have um, three different ways of calculating it. I'm just going to get me a laser pointer here. We have the aggregation method, which is just by the definition of amortized analysis. We have the bank method or the counting method, where we give each operation we can give multiple coins and then use that for later expensive operations. And potential method, which is the same thing as the counting method, just more mathematical and formal. You have to define a potential function, which is basically just um, creating a potential function for your coins. It's basically the same exact idea, but just this is more mathematical and formal, and this is more intuitive. Now, when we solve questions, as we saw in the last recitation, like in the test question we solved, we use mostly the bank method because it is the most intuitive and simplest. But you do need to know how to do all three in case they ask you specifically for one. Okay, so let's see the rest of the questions. Okay, so we want to implement a queue with two stacks. So first we have to describe a data structure that supports the following operations. So NQ, DQ, and is empty. We only have two stacks. We can't just use a queue. We have to implement it using two stacks. And we also have to calculate the amortized analysis runtime of each operation for our data structure. And they are very kind in this question, and they gave us the time beforehand. Not in all questions they give us the time. Sometimes you just have to do the best time that you can. But here they gave it to us that each operation occurs in O of 1 amortized analysis time. Okay. So here's okay. So first off, before I show you the answer, it is a recording, so you can pause it and try and solve it yourself. Um, I'm I'm just going to continue onwards. You can pause it and take a couple moments to think about it. I highly recommend, pausing it even for just 15 seconds and trying to think of an answer, and then going on with me um, to the um, to the answer. Okay, so the answer is we're going to use the two stacks. We're going to have one stack is going to be an insertion stack, S1, and the other one is going to be um, the DQ, taking out stack, which is going to be S2. So this is how we're going to implement all these methods is empty. We're just going to check if both of them are empty, we'll return that it's empty. If one of them still has elements, then our whole data structure still has elements, and then therefore it's not empty. NQ, we're going to put X into S1, because remember S1 is our insertion. DQ, if S1 and S2 are empty, we will return an error. If S2 is not empty, we're just gonna pop from S2 and return that one. Else, if S2 is empty, but S1 still has elements, we're gonna move all the elements from S1 to S2. Therefore, we're gonna flip the order of them and then take out from S2. So let's say an example here. We want to NQ5, NQ9, NQ2. Now let's say we want a DQ. So remember, we check if S2 is empty. If it has elements, we're just going to pop from it. But in this case, it's empty. So if we want a DQ, we have to move all the elements from S1 to S2. And then pop the the element at the head of the stack S2. So therefore, we pop 5 and return it. And you can see that 5 was the first element that we inserted to our data structure into our queue. So therefore, it also has to be the first that is also dequeued from our data structure. And therefore, we have first in, first out, because the first one in was also the first one out. Now, this is a question that you saw um, in the lecture, in one of the first lectures, but we're gonna now analyze it, amortized analysis, because back when you did it, you didn't fully understand why it's O of 1, because it's not O of 1 worst case, it's actually O of n worst case. But now we already know how to analyze things amortized. So let's now do that. The amortized analysis is we're going to use the bank method. We're going to give every element 4 coins, 4 shekels, one for putting it into S1, one for taking it out of S1, one for putting it into S2, and one for taking it out of S2. Now, this line is the most important line in the amortized analysis. You have to say that you have to explain why these shekels, these coins, are enough to cover all of the operations that we will do on that element in the future. So with a stack, you know that each element can be inserted once and also popped once. Um, but you don't always know that if it's a different data structure or something like that. It could be that you can do more operations on that, and you have to explain why. Each element that is covered, no matter which operations we do, it's always covered with these coins. So every element goes in and goes out from each stack exactly one time, right? Because um, uh, be we can't be popped from a stack twice. You can only be popped once. So therefore, these shekels are enough. So therefore, NQ and DQ are both O of 1, amortized, and we have just proved that it is all operations happen in O of 1 amortized, is empty happens in O of 1 worst case. And just a reminder, in worst case, NQ is always O of 1 in worst case. So really, this can be without amortized. It's really O of 1 worst case. And DQ is actually O of N worst case, but O of 1 amortized. Um, okay, so now we want a new data structure. This was actually in the homework. So describe a data structure that supports the following operations. Push, pop is empty, like a regular stack, but we also want minimum, getting the minimum element in the stack, but without taking it out of our data structure. Um, okay, what is the runtime in each of these for each of these operations in the worst case? Um, so as you did in the homework, really each one of these is O of 1. This is not even amortized, it's in worst case. That's just a reminder from the homework. Some people did this with 2 stacks. Here I'm just doing it with a pair instead of 2 stacks. Okay, so the solution is let's use a regular stack, except that every element that we insert is going to be a pair A, B, such that A is the actual element that we want to insert, and B is the minimum up until the point where we insert A. So let's just see an example. Um, let's say this is A and B. So here you can see that this is the element we inserted, and this is the minimum up until this point. This is the element we inserted, and this is the element up until this point. Minimum, we're just gonna take this. Um, we're just gonna take this. We're gonna take from the element at the head of the stack. We're just gonna take the B, and we're gonna return that. Is empty is just the same as a regular stack. Push, we're gonna calculate B, and then we're gonna push A and B into the stack. How are we gonna do that? A is just the element that we're trying to insert, and B is the minimum between the element and the previous minimum. So now if we want to insert, let's say 2, we want to push 2. So we compare 2 to the previous minimum, and then we take the smaller of the 2, and we push that as B. That's what it basically is said here. And then pop is just we we take this out of the stack, but then we only return A. We don't care about the minimum B, we just pop and return A. So let's see here, pop, we um, get it out of that stack, and we return only A. We don't return B. Minimum, we just look at the top, and we return the second element, like the second part of the pair, so therefore we return B. Okay, so every operation is O of 1 in the worst case, as we just saw. And the space is O of n. N is the number of elements that are put in, that are inserted. Because a stack can, in the worst case, hold all of them. Therefore, we need O of n space to hold all of them. All right, next question. And also a reminder, you can do this also with two stacks. You don't need to do it with pairs A and B, but that's how I chose to do it. For the presentation, it's a bit more intuitive and better for the animations. Okay, so now we have a new question, which is minimum Q. Before we did minimum stack, now we need minimum Q. So we need to describe a data structure that supports NQ, DQ is empty, and also supports minimum. Now, also, what is the runtime of all these operations in the worst case or amortized analysis? So I'm just gonna give a spoiler. This is a mistake in the presentation. NQ and DQ are gonna be actually in amortized. So let's just see. Take a second, maybe try and solve it yourself, or just think about it a little bit. Just pause the video for a second. Now I'm gonna continue, and basically the idea is just use those two data structures we just saw. Using two stacks, we can create a queue, and also we have a minimum stack. So we're gonna do the same thing where we're gonna use S1 and S2, two stacks to implement the queue, and each stack is gonna be minimum, so therefore we're also gonna have the get min operation. So NQ, we're gonna insert X into S1, but insertion of minimum, right? Just like we just saw. We NQ5, so we have pairs. And then we insert 9, and we check the minimum again. This is just what we just saw. Now DQ is gonna be the same. It's not gonna be pop like before. We need DQ, right? So we need to keep that first in, first out data structures. So we need to implement it with two minimum stacks, like we see here. And then this S2 is going to be the DQ stack. So let's see, we insert another element. And then if you remember, if you recall, we on DQ, we have to move all these elements into S2. And then we pop the topmost one and return that as DQ. But now here we have a slight issue that if we just took these elements as is and inserted them into S2, the minimum operation would be a little bit ruined. Because let's say we have 2 and 2, we insert 2 and 2, and then 9 and 5, we insert 9 and 5. But really in this stack, 5 isn't the minimum of all the elements below 2, S2. So therefore we want to do exactly like we want to treat this as a completely separate minimum stack. So therefore, when we pop from this stack, we only get the first element, A. And then when we insert it, we calculate the new minimum, B. So let's just see an example of DQ. We pop the top one, and then we have to create a new element and recalculate the new minimum of the S2 stack. So therefore, we insert that new element into S2, and then we do the same thing for 9 and 5, see how the 5 changes to 2, and then we insert that into the stack. And then same thing for 5, that we have to create a new element with 2 being the new minimum, and then we insert that. And then we obviously return that element 5 on DQ. Now, note that the minimum here in this stack is 2, right? The minimum up until here is 2. Therefore, on minimum, we check the minimum between both stacks, right? Because we could have more elements here, and we want the minimum out of all of the elements. So therefore, if there's more elements in here, let's say we insert 1 and 1, we have to return the minimum from this top element and this top element, because this top element has the minimum of all the elements um, below it, and this element has the minimum of all elements below it. So therefore, the minimum between the two of them is the minimum of all of the elements. So if we return minimum, we look at the two top elements and return the smaller of the two. That's what's said here. All right, now we have to calculate the complexity. So NQ, we know it is O of 1. In the worst case, we always just insert into S1. Now DQ is O of 1 amortized, exactly like um, a Q with two stacks, right? Because in worst case, we have to take all the elements here, could be n elements, and transfer them to S2, which could take O of n worst case. But if we calculate it exactly, I'm not going to do the analysis again here, but we're just like we did with a Q with two stacks, we also do we also can analyze it the same way. I'm not going to do it again just because it's the same exact thing as before. And minimum is O of 1 because we just look at the top of the two stacks. Therefore, it's O of 1 in worst case. All right, last question for amortized analysis for today. All right, minimum window. So the problem is as such. We have input, we have an array A, the size of n, and we have window size of k. Our goal is to find the minimum in each window of k consecutive elements. So for our first window would be A0, our first element, until A of k minus 1. The size of this window is k, and we want the minimum of all of these elements. And let's take a window, we basically move it by 1, then we move it by 1 again for the third window, and then the final window is A in the place of n minus k until A of n minus 1, till the end of the array, and we want the minimum of this window. And the output is we want an array B such that each uh, cell in B is the minimum of that window that we just saw. So B in the first place is the minimum of our first window. So let's just see an example. Here's our input array and our integer k, which is the size of the window. Therefore, our output would be 1, 1, 1, 1, and 2, 2. Why? Because this is our first window, and you can see that the minimum is 1. And then we slide the window, and we still have 1. Still, the minimum is 1. Still, the minimum is 1. The minimum of this window now is 2, and also for this window, it is 2. So take a minute to think about this before I solve it. First think of the naive way and then try and get to an optimal solution. All right, so I'm going to continue. Okay. First, our naive solution. For every window, we'll just scan the k elements and we'll keep track of the minimum, which would cost us for each window. There are O of n windows. We need to do O of n operations, therefore the naive way is O of n times k. If we just look at our window again, we just need to find the minimum out of these three elements. So we have to scan them and keep track of the minimum. And then we reset. When we get to this window, we have to scan all the elements again, which is very, very, very inefficient. So let's see how we can reduce this runtime. Now the idea is quite, like you probably hopefully guessed, it's based on the data structures we just saw, which is the minimum Q, right? Instead of scanning each time all k elements, we're just gonna NQ the next element, DQ the one that has left the window, and then we just we get the minimum in O of 1. which where therefore in amortized would be O of n. So let's just see it written out properly. We're going to use a minimum Q. We're going to do n operations of nq and n minus k dqs. Why n? Because we want to insert all the elements. We're going to actually do k nqs, and then we're gonna do find minimum, and then we're gonna nq the next one, dq the previous one, nq, and then minimum, and then take and then do nq on the next element, dq the element that has left the window, and then take the minimum of that new window, and so on and so forth. That's why here it's n nqs and n minus k dqs, because at the end we don't really need to dq the whole window, we can just leave it as is. And then after every insertion from the kth nq, we're going to find the minimum and add it to our output array. So here's the algorithm in Hebrew pseudocode, but you can write this exact same thing with English pseudocode if you want. Okay, so initialize the output B and the minimum Q, and then we will insert the first k elements into our minimum Q, and then we're gonna input Q minimum. So we're gonna take the minimum into that first place, right? That's the minimum of the first window, and this happens in O of 1. And then for each I, k until n minus 1, we're gonna dq. We're gonna take we're gonna dq the element that we inserted first. So the element that needs to leave the window, we're gonna take out the element I minus k. And then we're gonna nq the next element. We're gonna insert ai, and then we're gonna find the minimum in O of 1 with our minimum Q and insert it into our output array in the proper place. Then we just return B. So that was a very, very straightforward solution. If you didn't have that minimum Q data structure, it would be a little bit more difficult. There are other ways to solving it, but this is kind of a cool sequence of questions all building on top of each other. Let's just, before we finish, let's just calculate the complexity. We have n operations of nq, which is O of n minus k dq operations, it's O of n amortized, right? Because we showed in our data structure, dq is O of 1 amortized. So therefore, if we do n minus k operations that are O of 1 amortized, it's O of n amortized. And we have n minus k plus 1 operations of get minimum, which is O of n in worst case. Therefore, in total, it's O of n amortized. Okay, I hope that kind of cleared up a little bit more the subject, the topic of amortized analysis. With a cool couple of examples. Now I'm gonna stop the recording and record the next part of the recitation, which is linear data structures and also union find. So I will see you there.